Welcome back to eCoreAcademy, everyone. My name is Anita Raj, and I am one of the teachers and co-founders here, along with my younger brother, AJ Raj. As you can tell, we have a new Algebra 2 lesson today, and it's going to be a part 2 to our previous lesson on polynomials, linear factors, and zeros. Again, this is going to be a part 2, so a continuation, and we're going to finish off this lesson so we can move on to further lessons in this unit all about polynomials. In this lesson, we're going to be focusing on understanding relative minimums and maximums, and then we'll be looking at real-world applications. So you might be kind of wondering, what are relative minimums and maximums? Well, I'll be showing you on the following slides when we look at graphs of these polynomials, specifically cubics and quartics, and what these relative minimums and maximums are. So I just want to get right into the lesson because first we're going to be looking at some notes, then I'll show you a quick calculator problem, and then we'll be doing several real-world applications, and we'll throw in some challenge problems at the end. Before I get into it, however, I do want to just give a nod to this image I have here of some boxes. So you might be wondering, why do I have boxes? Well, these are typically like boxes you ship goods in, ship items, products, whatever in, and this is going to be the main focus of three or four of our real world applications. So just keep in mind that the theme in this is going to be these boxes, these three-dimensional, usually cubic, sometimes rectangular prisms, these boxes. So keep that in mind. Before I get into the video, I would really appreciate it if you all could like, subscribe, hit the post notification bell, drop a comment down below, and share it using all of our socials. It's very much appreciated. Alright, let's jump right into the video with our first slide, which is going to be notes on relative maximum and minimum values when we look at graphs of these polynomial functions. Okay, first let's go over what is a relative maximum. A relative maximum is a high point on a graph with respect to the points around it. So when we say relative maximum, remember relative, you also see words such as local. Relative means around. It means approximately. It doesn't mean when I look at a graph, this is the maximum point, this is the highest value of the point that the graph is going to have. Rather, it means in this area that we're looking at, this area that we're focusing on the graph, usually somewhere around the origin, in this area that we're focusing on this polynomial graph, this one point on that graph is like the highest point. It's like the peak, the apex in that area. That doesn't necessarily mean that has to be the highest value of the entire function, because remember, the function's continuous. It'll go from negative infinity to positive infinity, so it'll just be continuously increasing in most cases, or continuously decreasing. But in this area that we're focusing on, this is the highest point. This is the apex. So you can think of it almost like the apex. So I drew a little hill here. This is going to be the apex. And then just keep in mind that the function might be going like that, and it might be continuing downward like that. But in this area that we're focusing on, that is the highest point. So it's the relative or local maximum. Relative minimum is actually the flip side. So if you understand relative maximum, relative minimum should be really easy to understand. It's a low point on a graph with respect to the points around it. So just like we said, it's not the lowest point on the entire function. It's not the smallest point that the function has. Remember, the function's continuous from negative infinity to positive infinity because it's polynomial, which is a property of polynomial functions. You'll learn more about that in pre-calculus next year. But just keep that in mind. In the specific area that we're looking at, relative minimum is where the graph kind of dips. So I'll just draw a quick little diagram for you. If we have a graph that looks kind of like that, and then it dips like that, this could be your relative minimum if you're just focusing on this area right here. Keep in mind that the graph of the function is just decreasing towards negative infinity, but in this area that we're focusing on, where I drew the dashed lines, this is just your relative minimum. Alright, and these are just two notes that I do want to point out. Your relative maximum and minimum, when you're identifying them, they're going to be the y values. Because remember, I think this was addressed in pre-algebra. When you're asked for the relative maximum or minimum, you're asked for the value of the function at that point. When you're asked for the value of a function, you're actually being asked for the y value of the function. So whenever the y coordinate. So if ever we have a coordinate x, y, the y coordinate is always going to be the value of the function at a given point, at a given x. So keep that in mind. We give our final answers for relative maximum and minimums. We're giving the y coordinates. A second pointer, a function can have more than one of each. So a function can have more than one maximum or more than one minimum. And I'll show you, I'll just draw a little sketch of that. So maybe we have a function that looks kind of like that, and then it goes to infinity. Well, in this case, we could have two relative maximums. One could be right here and one could be right here. We would have two relative minimums, one here, one here. These are like the apexes of the hill or the peak of the hill, and these are the dips. These are the dips. So those would be our relative minimums, and these would be our relative maximums. So there can be multiple. Just keep that in mind. And right before we move into the calculator problem, whoops, I have all of this drawing on it. Let me erase that. But I just wanted to show you all a graph of what this would look like of a cubic polynomial, as you can see. Give me 1 second to just erase all this. So this is a cubic polynomial. As you can see from the equation here, our leading term is x cubed, so it's cubic. You can also recognize the shape, hopefully by now, with all the examples we've done. Cubics often look like this, or if they're reflected, meaning the leading coefficient has a negative in front of it. So if this was negative x cubed, it would look something like that. So that is your cubic. And this is the origin right here. This is 0. This is the origin. So we're focusing on this specific area. We're not looking over here because the function is just increasing to infinity, and over here where it's decreasing to infinity, we're just focusing on this one certain section. We're trying to identify the local or relative maximum. In this case, it's the point -1, 6, and then your local minimum, which is 3, -26. See how this is like the apex of the hill or the peak of the hill? It's where the function is like going upward. It's like the highest point of the mountain, or the function in this case, and this is like a valley. It's where the function will dip before it just continues on towards infinity. So that's it's shown on a more conventional graph. Okay, everyone, as you can see, I've changed the webcam view, so now you can see my TI-84 Plus calculator. And the reason I've changed the view is because I wanted to show you one practice problem on which we just very simply find the relative minimum and maximum of a function using the calculator, just so you know how to utilize it. Because if you are allowed to utilize this calculator on an assessment, it's going to save you a lot of time rather than actually have to graph it by hand or calculate it by hand. Okay, like I said, problem number 1, we're going to be finding the relative maximum and minimum of a given function. So as the instructions to the left say, use the TI to find the relative maximum and minimum values. And the function we've been given, you can see it's a quartic polynomial because the leading term is x to the 4th. And there are 4 terms in the polynomial. It is f of x equals x to the 4th plus 5x cubed minus 11x plus 1. And let's see exactly how we're going to start this. So first we want to enter in y equals, and then we want to adjust our window and graph. Before we even do that, we have to turn on our calculator. And just for good measure, you can always clear your calculator just so you're starting with a fresh plate. Mine is already cleared, so we're going to jump right into it. We're going to go to our y equals, which is right here. And in our y1, we're going to type this function that we've been given. So we've been given x to the 4th plus 5x cubed minus 11x plus 1. So we're literally going to type whatever we've just been given. Then we're going to go to our window and we're going to adjust it. For the sake of saving time, I'm just going to tell you to adjust your x min to -50, your x max to 50, scroll down to your y min, adjust it to -50, and your y max to 50. Just to save time, because this will help us see the whole graph so that we can see both the minimum and the maximum. Okay, so now we're just going to graph it. So we're going to hit the graph button here. We're just going to wait for the TI to graph it for us. As you can see, it's this blue line right here. It's a quartic, so it bounces. I know it's kind of difficult to see, but if you have your calculator, you'll see it looks almost like a W. So now that we've graphed it, let's see the next step. First, we're going to try to find the maximum. So for the maximum, remember, this is the relative maximum. So it might not be the maximum of this entire graph because, as you can see, the ends just continue on towards infinity. But in this area, we're trying to find the relative maximum. And if you see, it's like this little hump near the y-axis. That is the relative maximum. So we can see that there's one relative maximum in this quartic function. It's where there's a little hump that comes up, and then it goes back down, and then it goes on to infinity. We're trying to find what this maximum is, the exact point. So to find that, we're going to hit second, then we're going to hit trace, then we're going to hit 4 for maximum. Then we're going to do right and left bounds. So if this is asking me left bound, so I'm going to move to the left of where I think the maximum is, hit enter, move to the right of where I think the maximum is, hit enter, and then guess. So I'm going to go to where I think the maximum is, and then I'm going to be given an answer. And so if you see here, x is equal to negative 1.00 all the way to 1, we can just round this to negative 1 because the calculator is not always correct. I know it's kind of difficult to see. I'm going to tilt it up for you. So you can see it's negative 1. We're going to round that to negative 1 point blah, 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 blah. We're going to round that to negative 1. And then y is equal to 8. So our point, the relative maximum is negative 1, 8. But remember, when we're trying to give the final answer is the value of the function. And the value of a function at a given point is the y-coordinate. So our final answer would be 8 for the relative maximum. So let's answer the second part of the question. We have to find the minimums. However, with this function of a quartic, we have two minimums. We have one down here. We have another one down here on both sides of this little hump in the graph. So we need to find both of them. For minimum, what we're going to do is we're going to do second, trace, then we're going to hit 3 for minimum. It's right above maximum. First, we can find the one down here. So if it says left bound, I'm just going to go to the left of this minimum, hit enter, go to the right of this minimum, hit enter, and then go to where I think the minimum is, hit enter, and I'm getting negative 3.529208, and my y is negative 24.83, etc. So as you can see, the first minimum is exactly that, and we take the y-coordinate because, again, the value of the function is the y-coordinate, which is what we want. So we're going to just round this y-coordinate to negative 24.83. We're going to round it to hundredths. We also have another minimum we need to find. So let's find that by doing the exact same thing. Second, trace, 3 for minimum, except we're going to go and focus on this minimum here. So if we're doing left bound, I'm going to probably go up there, hit enter, go to the right of the minimum, hit enter, go to where I think the minimum is, hit enter. And I'm going to get 0.7. We can round that to 0.78. And then my y is going to be negative 4.837. We can round that to negative 4.84. And as you can see, that is the second answer. We're going to take the y value, round it to the hundredths. We're going to get negative 4.84. So that is how you use the TI calculator to find relative maximums and minimums. I would suggest you just find random equations, polynomial functions on the internet, and try to graph this, and then try to find the relative minimums and maximums for more practice. All right, everyone, let's move on to a real-world application. This is going to be our first one. Here's the problem. The design of a digital box camera maximizes the volume while keeping the sum of the dimensions at 6 inches. If the length must be 1.5 times the height, what should each dimension be? As you can see, it's a lot to unpackage, but keep in mind with real-world applications, you're looking at an actual scenario that can happen in real life. So we're talking about a digital box camera, usually a cube, maximizes the volume while keeping the sum of the dimensions at 6 inches. If the length must be 1.5 times the height, what should each dimension be? So let's break this down. Well, here's your solution pre-written if you want to copy it down. I'm just going to be walking through this with you again. Okay, we're told that this is a digital box camera. So this is going to be a 3-dimensional box. I'm just going to draw a cube, but we're not going to assume that this is a cube because then we would just be assuming the length, width, and height are all equal. But just for our sake, I'm just going to draw a cube. So there is my cube, and I'm just going to label its dimensions. Here we've got the length of the cube, here we've got the width of the cube, and here we've got the height of the cube. All right, so now we want to identify what we've been given. What information have we been given in this problem? By identifying what we've been given is going to help us organize our approach so much more. So we've been given that we're trying to find the maximum of this function because this maximizes the volume. So we're trying to find the maximum of whatever function we are going to make with this information. So maximum of function. Next, we are talking about the volume. Right here it says maximizing the volume. So we want to write the formula for volume. Volume is equal to length times width times height. Now, we're also being told that the sum of the dimensions is being kept at 6 inches. So the dimensions of any figure, in this case a cube, is going to be your length, width, and your height. Those are your 3 dimensions of this cube or rectangular prism. So in that case, the sum is, that means we're adding the dimensions. So length plus width plus height is equal to 6. That's what we get. And lastly, we're told that the length must be 1.5 times the height. So if we're using these variables for length and height, then we can write length in terms of height as length is equal to 1.5 times the height. All right, so where are we going to go from this? Now what we want to do is we want to pretty much write an equation, and we want to write an equation first before we even do that, we want to figure out what each of these variables is equal to. So we want to kind of write each of them in terms of one variable, so it's easy for us to combine like terms, and I'll show you exactly what we mean. So I'm just going to rewrite this. Length plus width plus height is equal to 6. I'm going to substitute 1.5h in for length, so 1.5h plus width plus height is equal to 6. I'm going to combine the h and the 1.5. Remember, there's an imaginary 1 in front of the h, so we're going to get 2.5h plus w is equal to 6. And if we subtract 2.5h from both sides, we can actually isolate the w and write it in terms of h, so 6 minus 2.5h. So now, if we want to write the volume, we get volume is equal to length times width times height, like we said. But if we write this all in terms of h, because now we have the width and the length in terms of h, we can write this as 1.5h, because that is the length, times the width, which we find out to be 6 minus 2.5h, times the height, which is just going to be h. What you can do with this then is you can actually plug this into your graphing calculator, and you can find the relative maximum using the method I showed you in the previous problem. So if you plug this in, for the sake of time, I'm not going to do that for you, but you can actually, this is supposed to say graphing calculator. I don't know why I put graphing maximum. But so you're going to plug this in your graphing calculator, and then you're going to find that the maximum is going to be equal to the point 1.67.68. And how are we going to understand this? How are we going to interpret this? Well, this x is going to be your height, because remember, in our equation here, this is what we plugged into our TI calculator. H is actually x in this case. If you want to think of it as x, y, h is like our x, so it's going to be our x coordinate, it's going to be our height, and then your y coordinate is going to be your volume, because that was your y in this case, so your volume. Using this information, we should try to figure out what each dimension is going to be. Well, height's pretty easy, because height is just equal to x, which is equal to 1.6 inches. That looks like 16, 1.6 inches. Length is going to be equal to, well, we had 1.5h, pardon me, so we're going to have 1.5 times 1.6, and if you multiply those two, you'll get 2 inches. And then lastly, you'll get width is equal to 6 minus 2.5 times h, which is 2.5 times 1.6. Is going to be equal to 6 minus 4, because 2.5 times 1.6 is 4, which is going to give you 2 inches. So this is going to be your final answer. These are each of your dimensions. All right, moving right along, because we have quite a bit to cover. Let's go to our real-world application number 2. In this problem, this one's going to be a bit different. Here's the problem. A metal worker wants to make an open box from a sheet of metal by cutting equal squares from each corner, write expressions for the dimensions, make a function, and find maximum value. Okay, these are the 3 things right from the get-go we need to understand what we want to do. We want to write expressions for the dimensions. So we're going to have 3 dimensions again, length, width, and height, and you want to write expressions. So you pretty much want to rewrite each of those variables in terms of one variable, like we did in the last problem with height. You want to make a function. Easily we can do that by multiplying each of the dimensions together, because volume equals length times height times length times width times height. Then we want to find the maximum value, and we can easily do that by using our TI calculators. Here's your solution. So here's an image that I'm going to provide to you. So pretend this image was part of this problem, like this image was provided to you with this problem. I actually drew this. I know my art skills are just amazing. But here is going to be your open box. So remember, an open box doesn't have a lid, like I tried to show in this little drawing here. It doesn't have a lid. It's an open box from a sheet of metal by cutting equal squares from each corner. So this metal worker had a flat sheet of metal, just flat, and what the metal worker did was he or she cut from the corners square boxes and then folded those boxes up so that they could create like a container, but it doesn't have any lid over the top. So what I've shown here is that this is going to be your length, and then here is going to be your width, so 16 inches. Sorry, I'm going to flip it the other way. This is going to be your width, 12 inches, your length, 16 inches, and this is just a net. Again, a net is like when you take a 3-dimensional shape and you lay it out flat. And then these are going to be your squares right here that are being cut from the corners. Like this here is going to be cut from the corner. This is going to be cut. This is going to be cut. This is going to be cut. And the dotted lines are going to be folded inward. So if you see, what I did was I labeled each corner of the square as x, because remember, all sides of a square are equal. So each of these sides are going to be known as x. So we're trying to so we just need to understand that. Okay, so now we're gonna I'm gonna show you the solution. It's actually not too much work. Yeah, so I'm gonna run through that again with you. And before we start, I just want to make sure we understand that x, which is here, is going to be the side length of square cut out to fold metal. I think we already understand that by now. Now we want to write, using x, we want to write the 3 dimensions of this open box. So we're going to have a length, because again, it's a box. It can be a cube, or in this case, it's going to be a rectangular prism, pardon me. So we're going to need a length, a width, and a height. So we have to write these in terms of x, which is going to be the side length of the square that's going to be cut out from the box. All right, so length should be right here, 16 inches, right? So typically, we would just write 16 inches and be done with it, but keep in mind that we're cutting out a box from each end. We're cutting this end out, we're cutting this end out. So technically, if each of these ends is x, if this is x, we're cutting x off, and we're cutting x off here, then we're going to subtract 2x from it, because we're removing those 2 boxes from each end. Same thing with width. Our width is going to be 12, and we're going to be doing the same thing on this side. We have 2 boxes here, x and x, and we're going to be subtracting 2x. And lastly, the height is just going to be x. And you might be thinking, why? Well, if we fold the box upward like this, the side length of that square is going to be the length of how much we're going to have like standing up. So it's kind of hard to show you this way, but if I try to fold this box inward like that, x is actually going to be the height of the box. So just think of it logically like that. If you fold it upwards like this, we're cutting out a box that actually stands up like that, and the side length of the square is x. That's going to be the height. So we have these 3 dimensions, and we've written them all in terms of x. Now we're going to find which we did. We wrote expressions for the dimensions. Now we're going to make a function. So volume is equal to length times width times height. So our length is 16 minus 2x times the width, which is 12 minus 2x times the height, which is x. We're going to plug this. We're going to graph this on the calculator. Graph on calculator. Find, and then we're going to find our relative maximum, because again, we were asked to find the maximum volume that we could possibly make. Find relative maximum. And what you should, I'm not going to do it for you. You should be able to do this by yourself at this point. You should get the point 2.26, 194.07. So how are we going to interpret this? So, well, the 2.26 is going to be x, remember, because the x coordinate. In this case, x was our height. The height was also the side length of this little square box that we had. So that's what this is what the 2.26 is. It's the length of the side of the box. This 194.07 is going to be your volume. So your volume at the end of the day, which is what we wanted our answer to be, is going to be 194.07 cm. Actually, I just realized this. In my work, I put centimeters cubed, but on this diagram, I put inches. So I actually mixed up my units. This should be inches cubed. So sorry, in my work that I showed you previously, it said centimeters cubed. Don't mix up your units. This is inches cubed. All right, let's move right along to the next problem, our last real-world application that has to do with these boxes. I know boxes are so much fun to work with, but here's the problem. A storage company needs to design a new storage box that has twice the volume of the largest box. So their largest box's dimensions are 5 feet long, 4 feet wide, and 3 feet wide. 3 feet high. So 4 times 3 times 5 is equal to 60. So they need a new storage box that's twice that volume. So it needs to be 120 feet cubed. The next box, or the new box, must be formed by increasing each dimension by the same amount. So find the increase in each dimension. So you want the new box to have a volume of 120. But when we increase, and to make a greater, to get a greater volume, you need to increase the dimensions because you're multiplying them together to get the new volume. But when we increase the dimensions, we're being asked to increase them by the same amount. So if I'm making now, the length is right now equal to 5. If I want to make the length equal to 6, I'm adding 1 to it, which means by this requirement, I need to add 1 to the width and 1 to the height. So it needs to be constant. All right, knowing that, this is the solution for you. And we're going to walk through that all over again. So I just want to rewrite that, that width is equal to length times width times, volume is equal to length times width times height. Knowing this, we can figure out what the old volume is of the previous largest box, which I literally just said was 60. So that's 5 times 4 times 3. We're just multiplying the 3 dimensions is equal to 60. So this is going to be your old box. Our new box, like they said, is double the volume of the old box. So that's going to be 120. So this is going to be your new box. Pretty straightforward, pretty easy. Now we're going to try to understand how we're going to plug this into the TI calculator. Well, let's declare a variable x that we're going to put in. This is going to be equal to the increase in each dimension. So this is how much we're going to be adding to each dimension so that when we multiply the new dimensions together of the new box, we get 120 cubic feet as our new volume. So volume is equal to length times width times height. So let's write this as 120, which is the volume we're looking for. So the length is going to be, the old length was 5. Now we're adding some x units. We don't know. X is just going to be the increase. Maybe we're increasing by 1 foot or 2 feet. Who knows? So we're going to have 5 plus x times the width, which is 4 of the old box, plus x times 3 plus x. As you can see, I hope you're realizing that we're adding the same amount to each dimension. These are the old dimensions. Recall that. We're going to put this in our graphing calculator. And when we put this in our graphing calculator, we can't just type in 120 equals blah, 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 blah. Remember, we have our y1, our y2. That just doesn't work. So what we're going to do is we're going to split this up. We're going to get y equals 120. We're going to put that in our one y equals. And then in the one that follows it, we're going to put in the rest. So 5 plus x times 4 plus x times 3 plus x. So we're going to put these in two separate y equals. You can put this y equals 120 in your y1 and then the second equation in your y2 to make it easier. Then what we're going to do is we're going to find the intersection, and you're going to do this on your own. You should be able to find the intersection pretty easily. You're going to find the intersection, and the intersection you should be 120. That's the point. So the 1 is going to be how much it should be increased, because recall how much it should be increased. Because recall, 1 is your x coordinate, and in this case, x we declared was going to be the variable that was going to represent the increase in each dimension, which was what we wrote right here. So if there's an increase of 1, x is going to be equal to 1 foot increase in each dimension. So that's answering the question that we were asked. If we want to go a step further, we can identify the new dimensions. The new length is going to be 5 plus 1, which is 6. New width is 4 plus 1, which is 5. And new height is going to be 3 plus 1, which is 4. All right, solve that problem. Let's keep on going. We've got 2 more left. So here's our next real-world application. This does have to do with boxes, but it's honestly so much easier because it's just going to be looking at your skills of understanding, applying volume formulas along with multiplying polynomials. Okay, so this is our next real-world application. A rectangular box is 2x plus 3 units long, 2x minus 3 units wide, and 3x units high. What is its volume expressed as a polynomial? So this should be pretty easy for you. Here's the solution pre-written. I'm going to run through this very quickly with you. So we're going to rewrite the volume formula. Volume is equal to length times width times height. I think I've drilled that in your head by now with this lesson. Now we want to identify what each of these variables is equal to because we've literally been given it in the problem. So the length is equal to 2x plus 3 units. 2x plus 3 units. Our width is equal to, remember I'm taking this right from the problem, 2x minus 3 units. It's almost like we're identifying our givens like we did in the previous problem to help us organize our information. And the height is equal to 3x units. Like we said, volume is equal to length times width times height. So volume is going to be equal to, we're going to substitute each of these in for the different variables or the different dimensions. So volume is equal to 2x plus 3 times 2x minus 3 times 3x. If you look at these guys right here, these sets of parentheses, they're almost like conjugates, because if you see, it's literally the same expression but different signs. And what you're going to see, they have a special property where the middle terms will cancel, so that you'll see that the x terms will cancel. So if I literally, all I have to do is just multiply this out. So 2x times, I'm going to multiply these two first parentheses together first. 2x times 2x is equal to 4x squared. 2x times negative 3 is negative 6x. 3 times 2x is plus 6x. Plus 3 times negative 3 is equal to negative 9 times the 3x. We just got to bring it down. You see that these cancel with each other. Remember how I said the middle terms will cancel. You can rewrite this as 3x times whatever's left in this set of parentheses, which is the 4x squared minus 9. Then we're going to distribute the 3x, and we're going to get 3x times 4x squared, which is 12x cubed, minus 3 times 9 is 27x. And this is what f of x is going to be equal to. F of x is just another way to say volume is equal to, whoops, that is a really bad x. F of x is equal to that many units cubed. All right, that was, we breezed through that, but it was pretty easy. And this is going to be our last problem. Here's a challenge problem. It doesn't really have to do with what we did with what we've done so far, but it does have imaginary numbers, and I did want to bring back a concept we've learned just to reinforce it. So we're being asked to find a fourth degree polynomial function with zeros 1, negative 1. I'm sorry, so for some reason the negative sign got separated from the 1, but it's a negative 1, I, and negative I. Write the function factored form. So I'm just going to rewrite the zeros. Ooh, zeros. What are zeros? Zeros are also factors. So keep that in mind. So here are zeros, 1, negative 1, I, and negative I. I'm writing it because it kind of got cut off for some reason with the formatting. So these are going to be our zeros. We're being told to write a fourth degree polynomial, so a quartic. And we are just told to leave it in factored form, so we don't need to multiply it out. So here is your solution pre-written. I'm going to be running through this again. If you see, your linear, so your zeros, like I said, are your factors. So your linear factors are going to be in the form of x minus b is equal to 0. Recall that b was going to be your actual 0. So in this case, 1 would be b, negative 1 would be b, I would be b, negative I would be b. So that is your linear factor. If I add b to both sides, and remember, linear factors, if you set, they're also zeros of the function, so I can set it equal to 0. So if I add b to both sides, the b's on this side will cancel out, so I get x alone, and then x is equal to b. So in this case, our x's are going to be equal to our b's. Just keep that in mind, and this will give us our zeros. All right, so let's apply this to this problem. So a fourth degree polynomial is equal to 4 linear factors. Because if you think about it, if you multiply the leading terms together, you got to have x plus blah, 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 times x plus blah, 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 times x plus blah, 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 times x plus blah, 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 and you're going to end up getting x to the fourth. So that's why we're going to have 4 linear factors, and it works out perfectly because we've been given 4 zeros, which are also our linear factors. So if we have 1, we're going to rewrite this in terms of x minus b, so we're going to have x minus 1. Negative 1 is going to be x plus 1, because remember, negative times positive is equal, negative times negative is equal to positive. I is going to be x minus I, and then negative I is going to be x plus I, because again, negative times negative is positive. Well, if we combine all these together, we can write our function f of x as equal to just our factors. We can just leave it in factored form because that's what the problem said. So x minus 1 times x plus 1 times x minus I times x plus I. I'm going to put that in the next line, x plus I. So this is our answer, and you can see that it is in factored form. We just left them as linear factors. So factored form. That is it. It's not that difficult of a problem. Hope you got through it with me. All right, that's all I have for you today. Thank you for sticking with me. It's a pretty good video. We went through a lot of practice problems, so hopefully you're comfortable with all those real-world applications I know your teachers are going to put on the test, but make sure that, just show them that they can be confident in you because you know what you're doing. All right, so here's our website and our Gmail, so please reach out and check those out. You can definitely, please feel free to leave a like, a comment, to subscribe to our channel, to turn the post notification bells on, and to share using our social medias. All of that is appreciated. Well, I'll be seeing you in my next Algebra 2 video. Thank you for joining me.